So parallel plate energy problems. First of all, a little bit of review. We said for parallel plates, first of all, the voltage, it's given by the battery. Next unit, when we look at circuitry, we'll actually calculate how you can figure out what the voltage is. But for now, I'll give you the voltage in the diagram somewhere, typically. And we said this. We recall that for a test charge placed at a point whose voltage is known, we can find potential energy. Well, on your formula sheet, we defined voltage as energy per coulomb. Actually, I think on your formula sheet, it was change in voltage and change in energy. Oh, and on your formula sheet, instead of using PE, they use E with a little subscripted P, but I'm going to use PE for potential energy because E also means electric field. I don't want to get it mixed up. Cass, can you get the energy by itself for me? Yeah. Potential energy is QV, and the change in potential energy is Q times the change in voltage. That's not directly on your formula sheet. Well, it is if you get the energy by itself. That is a very handy version of potential energy to use. Remember I told you that voltage was kind of like height? This, don't write this down, is sort of the equivalent of the mgh of potential energy for gravity. QV is sort of like mgh. It's going to behave very similarly. Really? Yeah. Example 1. Example 1 says, find the work done by an external agent. When I say external agent, Mateo, you can imagine there's a little invisible leprechaun on the page or something. Okay? And it's moving a positive 2.5 microcoulomb charge from the negative plate to the positive plate. Mateo, what's the charge on this little guy here, positive or negative? What's the charge on the voltage up here, positive or negative? Like or unlike? Like, repel or attract. In other words, this does not want to go up, it wants to fall down. Mathematically, moving that positive to the top of the voltage, that's the same mathematically as lifting an object up and giving it potential energy. When I let go of this object that I've lifted up, what will the potential energy turn into? You all know this, huh? In fact, when it hits the ground, all of the potential has turned into kinetic. I have to do work to lift it up because it doesn't want to go up. I'm going to have to do work to lift that positive charge up. It doesn't want to go up. Mateo, what does this question want me to find? Okay, so work is going to be change in potential plus change in kinetic. Oh, wait a minute. It says assume the charge begins and ends at rest. So Renzo, no change in kinetic. Now, if this was how much work to move a point charge towards or away from another point charge, we would go, what's change in anything? And you would say, and then I would go, so it's going to be PE final minus PE initial, and then I would go, that's KQ1, Q2 over R final minus KQ1. I'd be bringing out the ditto marks. We'd be typing like crazy, but are we between 2 point charges here? No. We have one charge and a plate. Hey, Mateo, that right there. And here's the beauty. That's actually the entire change in potential energy. If I use the entire change in voltage, I don't even need to go final minus initial. You want to know how much work it's going to take? Apparently, it's going to take Q times the change in voltage. Mateo, how big is the charge that we're moving? What's the total voltage that we're moving it through? I think I can do this in my head. 2.5 times 12. 12 times 2 is 24. It's going to be 30. 3 times 10 to the negative 4 or negative 3? Negative 4? Yeah. I'll go to 2 sig figs. 3.0 times 10 to the negative 4 units. Work, Mateo? Yeah. Good sneeze. I'm going to argue, and this pun is intended, that's way less work than finding work between 2 point charges. This is one of the other reasons that electric fields between parallel plates have such a nice mathematical consequence. The fact that the electric field is constant means the force is constant, means I can bring in shortcuts for energy, for work. That first example that we just did, Luke, was mathematically like lifting something up. Example 2 says this: find the final speed of an electron beam if it's accelerated by 125 volts. There's no external agent, so here energy is conserved. Luke, my friend, what's the charge on an electron, positive or negative?
Negative.
What's the charge on this voltage right here?
Negative.
Like are going to repel. This is going to want to accelerate that way. You know what? If you turn your head sideways, this is exactly the same as me dropping this. This is going to want to accelerate down. Why? Because that's the direction of the gravitational field. This is going to want to accelerate to the right. Why? Because the electric field is pointing to the left, and the electric field is which way a positive would want to move. So if a positive would want to speed up going to the left, a negative is going to want to speed up going to the right. The weakness of my gravity analogy is sometimes stuff can fall up. We have 2 different polarities. Is this question asking how much work? Luke, my friend. What's it ask me to find? Did it say speed or did it say velocity? I picked that word carefully. That's me suggesting scalar approach. You know what? This is just like dropping an object. There is a change in height. I did tell you that voltage was just like height, sort of. There is a change in speed. This is a job for conservation of energy. G. You could probably also actually solve this by finding the force on the charge and then by figuring out the acceleration. Oh, nope, you couldn't find the acceleration because I didn't give you the mass. Oh, I did give you the mass. It's an electron. And you could also go VF equals VI plus 8, or VF squared equals VI squared plus 2AD. You could do it that way, but this is going to be cleaner. Hey, are any of these 0, Luke?
Yes.
What? Are any of these 0?
KI.
Starts VI as 0. Okay. Now, right here, this is sort of like landing on the ground. When you landed on the ground, what was your final potential energy?
0.
Now, where my gravity analogy breaks down is we've dug a hole in the ground. It's going to keep going. In real life, if you dug a hole in the ground, it would be speeding up as it fell into the hole and it would keep speeding up. Here, it's not going to speed up once it leaves. It's used up all of its potential energy. It's all turned into kinetic. Now it's going to keep going in a straight line at a steady speed. So my gravity analogy is breaking down a little bit, but hopefully still kind of okay. Hey, what's kinetic energy been, Luke, since physics 11? Yep. Potential energy, this is electric potential energy, so don't say MGH. Oh, hey, what was our handy-dandy schmandy shorter version of electric potential energy that we could use if we knew the voltage? This, Luke, is the equation that I warned you about a few weeks ago when I said there is going to be an equation that has a V and a V in it. And this is why my college prof always had us put the big wings on voltage so that we wouldn't get voltage mixed up with velocity and cancel out the V's. Speaking of, how would I get V final by itself?
Times a 0.5 over.
I'm going to times by 2 or divide by 0.5. I'll times by 2. Divide by,
The mass.
and then?
Squared.
Yep. Cool. You said take the QV, times it by 2, divide by the mass, square root. All right. 2. They didn't tell me the charge. It's an electron. Good. You realize I've given you that. What is the charge on an electron? Luke, what's the voltage we're traveling through? Now, ready? If I could call the voltage negative, I would also call the charge negative because it is an electron and we are doing scalar. But am I taking the square root of something?
Yeah.
Don't I want the inside? You know what? For this particular here, you want it to be positive, so don't freak out about the signs. Just take the square root. So call it 125, okay? Divided by m. They didn't tell me the mass. It's an electron. It's on your sheet. It's 9.11 times 10 to the something. Negative 31? Electrons are booking it. You're going to get an answer at least 10 to the 5th or 10 to the 6th or 10 to the 7th. In other words, if you do this and you get an answer of like 38, you've really messed up. Electrons move far faster than our eyes can spot. Oh, if you get an answer bigger than 3 times 10 to the 8th, faster than the speed of light, you probably forgot square root, because that's by far the most common sloppy mistake on this. What do you get? How fast is it traveling? 6.6 times 10 to the 6th. Anybody else? Yeah? Meters per second. Mr. Dueck. What, Derek? You said that we can't go faster than light. Yeah, I said that. Mr. Dueck. What, Derek? I'm pretty sure that I could actually calculate how big a voltage I needed to put right there that would give me an answer here that would be faster than light. And once I know that voltage, why couldn't we just build something like that and go faster than light? All right, Derek, that's a good question. Do you see the argument, Derek, my friend? You're saying if I bump that up, I can go faster and faster? You with me? You've been totally zoning out? I've been making fun of you. So you ready? Put your pencil down, look up. We're going to do this again. Mr. Dueck, what, Derek? You just told me that this speed can't go faster than light. It's true. Mr. Dueck, couldn't I just bump that voltage up? And if I bump this voltage up, this is going to go faster. Surely there must be a voltage that I could put there where this will be bigger than 3 times 10 to the 8th. Einstein was wrong. No, Derek, Einstein was not. Because as you go faster and faster and faster, what happens to the mass of objects as they approach the speed of light? They also increase. Sorry, the universe takes care of itself. You can't. You go ahead, bump up the voltage. All you're going to find is actually this is not the mass that you'll be using. The electron will behave as though it has a much larger mass. Remember all that stuff that we did in special relativity last year? Okay. So, we'll write this equation in our box. It's not on your formula sheet. It comes out of conservation of energy. It says if you're accelerated from rest by a voltage, all of your potential turns into kinetic. All of your potential energy turns into kinetic energy. And anything there, to me, as far as I'm concerned, Renzo, is fair game to ask you to calculate. Here, I gave you everything and said, how fast? I would have no problem saying, well, how fast do we want to go? How much voltage do we need? That kind of a deal. Luke, in answer to your question, that's why I said absolutely, don't worry about putting negatives or positives in, because you're going to want to take the square root. Yeah, just don't worry about it. But don't confuse V with V. That's the big challenge. Turn the page. Let's take it one step further. Nick, here we have an electron already moving at 5 times 10 to the 5th meters per second and enters a set of accelerating plates. How fast is it traveling when it leaves the plates? Nick, this is just the same as lifting an object up, but instead of dropping it, you're throwing it down, so it already has some kinetic energy. But all of the potential will also turn into kinetic. Nick, what's this question want me to find? Speed or velocity? suggests a scalar approach. Again, if you kind of turn your head sideways, there is a change in voltage, change in height, change in speed. This is a job for conservation of energy. G. KE initial plus PE initial equals KE final plus PE final. Nick, are any of these 0? Are we ever at rest? Not this time. So I can't cross out KE initial or KE final. Do we ever hit the ground, so to speak, metaphorically? Where? Yeah. Right? This is ground level. Voltage is sort of like height, sort of. And so after that, you've used up all of your potential. You'll still have kinetic to keep going in a straight line at steady speed. Okay. A half m v initial squared plus q change in voltage equals a half m v final squared. Nick, what am I trying to find here? Which one of those v's? Yeah. You know, Nick, I think what I'm going to do is I'm going to just calculate this. I'm not going to try and get the VF by itself. And then once I get that as a number, then I'll go times by 2, divide by m square root. This is about as much algebra as I want to do. I could get the V final by itself, but it'd be kind of yucky. Okay. 0.5 m. It's an electron. (9.11 times 10 to the negative 31). Yes, I think. V initial, 5 times 10 to the 5th, says the question. Don't forget the squared, because, that never happens. Plus Q, the charge. It's an electron. Yeah. Ooh, be careful, Nick. What's the change in voltage that we're traveling through? I'll give you a hint. It's not 600. What is the change in voltage that we're traveling through? What? 500. See it? Starting at 100, ending at 600. What's the change in voltage? Okay. That is going to equal 0.5 m V final squared. Let's crunch that. .5 times 9.11 times 10 to negative 31 times 5 times 10 to the 5th squared plus 1.6 times 10 to negative 19 times 500. Typo. Times 500. Did I make another typo? A half m v squared plus q v. Do you get 8.01139 times 10 to the 17th? Okay. I'm running out of room. I'm going to have to go up here. V final is going to be the square root of 8.01139 times 10 to the negative 17 divided by a half m. It's an electron. Oh, look here, I divided by 0.5 instead of timesing by 2. Same thing. Divide by bracket 0.5 times 9.11 times 10 to the negative 31. That's wrong. I'm going faster than light. Oh! What's the last thing I have to do? Square root. Almost would have forgotten. Do you get 1.33 times 10 to the 7th? Cassidy, does that value match what I told you is typical values for moving electrons? I said, yeah, 10 to the 5th, 6th, or 7th range. Okay. Mr. Dewick, why did they give me this distance? I didn't need it. Because I could have done this differently. I could also have treated this completely as a force and an acceleration question. But I think this lends itself best to energy. And believe it or not, we've almost invented TV. Well, okay. What TV used to be. How many of you have ever watched a TV where when you look at it from the side, the screen was curved and then there was something big sticking out the back? Like, how many of you ever watched a TV, have watched one of those? Oh, thank goodness. Because in 3 or 4 years, only half the hands will go up, and a few years after that, people are going to be, what are you talking about? By the way, you already are familiar with an expression that probably you have never actually physically used. When they don't want you to change channels, they say to you, don't touch that. They don't say don't touch that remote. What do they say? Don't touch that. Word begins with the letter D. They don't say don't touch that dial. Have any of you ever used a dial on a television? I have. Have any of you ever used a TV that had a dial on it? Maybe in cheap hotels, right? I mean, that's about where I started. That's where they kind of migrated to. So, how does a TV work? Don't write this down. I'm going to muck this diagram up like crazy to explain how it works, and then we'll do a simplified, cleaner version. Okay? A CRT is a cathode ray tube. That's the abbreviation. Cathode ray tube is called a CRT. And in the simplest cathode ray tube, a beam of electrons is accelerated by one set of plates, deflected by another, and it hits the screen, which glows. I'm going to zoom in. Here is the guts of an old-style television. What you would do is you would have a set of plates, and you would charge it negatively, lots of negatives, a whole bunch of like charges. What would those like charges do? And so what would happen is electrons would just get shot off. Don't write that down. Now, that's yucky and messy, so what you would also do is you would install a negative plate right there, and another negative plate right there. And what that would do is it would basically push the electrons in a nice straight stream right to the middle. That's an electron gun. That's a cathode ray. That's step one. You want to get a nice stream of electrons. Oh, and you want to accelerate them. So you would charge this plate. So you have that negative plate on the left and the positive plate on the right. They're going to come flying out. And you make a really, really small opening so only a very fine stream of electrons can fly out. The electrons will go this way. Now, on the back of the curved screen, on the inside of the screen, you paint it with a very special paint that will fluoresce, that will glow like a little dot when an electron hits it. With our current setup, we would get a great big white dot in the middle of the screen. That's why the old black and white TVs, when you turned them on, for a few seconds, there was always a big white dot in the middle of your screen because the machine hadn't warmed up yet. Okay? Oh, and I should point out that you're sitting right here, so this is what you're seeing. Okay? So we already have the ability to put a dot on the screen. What would be really cool is if we could put that dot anywhere we wanted. Because we can put that dot anywhere we wanted, well then, Nick, we can start to draw a picture, and if we're quick enough, your eye won't see it as a bunch of separate dots. If we draw it really quick, your eye will just form it into a single coherent image. So there's a second set of plates. These ones here, these are the deflecting plates. Nick, what's the charge on this top plate? So as an electron comes blazing through, it's actually going to get deflected up. It'll hit there. Now I can make that dot light up. What if I bump up the voltage? It'll deflect even more. What if I lower the voltage? It'll deflect even less. Oh, you know what? We're plugged into alternating current, so what if I flip the voltage? It can deflect down there too. And by doing this very, very quickly, I can turn on or off a whole bunch of dots. Oh, hit the wrong button. I can turn on or off a whole bunch of little dots on the inside of this fluorescent screen. This is for black and white TV. We'll talk about color in a second. Okay. Oh, in fact, what I'll do is I'll paint an image, but I'll do it so fast, I'll paint 60 images every second. That's why we say TVs have a frame rate of 60 hertz. And if I paint 60 images every second, even though they're all a series of still images, the same way any cartoon that you've ever watched is a series of still drawings, the same way any film that you've ever watched is a series of still drawings, if I project them quickly enough, your eye will smoothly fill in the gaps and you'll notice no gaps. Be there in a second, Derek. I can also get not just black and white, these were the original from the 1930s. I can also get grays by changing back here how fast the electron gets accelerated by changing this voltage. If it has a whole bunch of energy, when it hits the phosphorescent plate, it'll make a dark dot. If I give it less speed, less energy, it'll make a gray dot. And so now I've got grayscale images. Now this is a bit of a fib. We're missing a set of plates. All this does is deflect it up and down. I would also want to deflect it left and right. So right here, there would be yet another set of plates, but these plates would be angled this way. And I could charge this one up positively, this one up negatively, and I can bend an electron left, right, as well as up, down. And I can put an electron, a glowing dot, anywhere I want to. You had a question?
So the signal that you get from the TV station is control the voltage of the plate?
The television camera, the originals, not the new digital, the old analog ones, turned physical light into an electric current and voltage. They damped it down. They turned that into a wave. When it hit your antenna amplified that same voltage back up. And because that voltage and that electromagnetic signal was directly proportional to the image that was coming in to the camera, you'd get that same image popping out the other end. It's actually surprisingly clean and simple, the old analog way to do it. Now, there's weaknesses. I told you that the electric fields are a little inconsistent on the edge. You're going to get some blur. Also, all of your TVs have to have this big thing sticking out the back to fit the electron gun and the plates. That's why you had that big bulb sticking out the back. None of this would work with mobile technology. You would not want a big thing sticking out the back here for your electron gun. Also, this took a tremendous amount of power. Your TVs take a lot of wattage. Doing that would drain the batteries on these very, very quickly. So we'll talk about how LCD works later on in class. I'll show you how that works, but this is how the old style used to work. Oh, for color, you have 3 guns. One red, one blue, and one green. There, now we've invented color TV. Okay, is that all right? Let's simplify this down a little bit. So if you want to, you can draw a little stick figure of somebody watching, just to let you know we're talking about the image that you see on that end. And then what I'd like you to do is put a number 1 with a circle around it right there. This is the first thing we're talking about. That's location 1. Location 1. Electrons, my abbreviation for electrons is E minus, are accelerated. That's why this is called a cathode ray tube. A cathode ray is a bunch of electrons. They didn't know they were electrons when they were first looking at this, so they called it cathode rays, and then later on they learned, oh, those are electrons. Location 2. Oh, you know what? I'll change colors just so it's easier to spot. Location 2. The electrons are deflected up or down, left or right, except I only have up-down plates here. So electrons are deflected U/D, up or down, L/R, left or right. Location 3, electron hits fluorescent, if you don't know what the word fluorescent means, glowing screen, and makes a dot. Put a bunch of those dots together and your eyes will see that as a picture because your eyes are just trained to look for pictures and everything, right? Yeah.
There's only one cathode ray in a series.
In a black and white, 3 in a color. Here's a video that explains it as well. Here's a side view. Here you can see the whole procedure. Here's our cathode ray. It fires out electrons. This focusing anode here would be charged in such a way that it would make the electrons all get pushed or pulled towards the middle. Then we have a vertical set of deflecting plates that deflects the electron up or down. We have a horizontal set of deflection plates that deflects the electron left or right. And you can put a dot anywhere on this screen that you want. TV. Example 5, last one. Sarah, what does A want me to find? Where? Situation A, we're talking about the speed right here. Okay. Did they say find the speed or did they say find the velocity? Suggests a scalar. Oh, you know what? This is the same thing as that energy. This is just like dropping an object in a gravitational field. We're dropping a charged object in an electrical field, and all of its potential energy will change into kinetic energy. PE initial plus KE initial equals PE final plus KE final. Sarah, are any of these 0? Yep. And PE final, because we're treating that right there as though it's the ground. So you got no more potential energy. It's all turned into kinetic. Oh, you know what, Sarah? We're going to use that QV, much nicer version of potential energy. This is one of the reasons voltage is so handy. Equals a half mv squared. In fact, we're going to end up with Luke's equation, I think. Luke said times by 2 divided by m square root. V is going to be 2 times Q times the voltage divided by m square root. V is going to be the square root of 2Q. Oh, it's an electron. 1.6 times 10 to the negative 19. V voltage. I've scrolled down. Sarah, how many volts are used in the electron accelerating gun portion of this?
1200.
So this is why TVs took a fair bit of power. There's a lot of voltage going on in different locations. Divided by mass. It's an electron. 9.11 times 10 to the negative 31. How fast is this electron, are these electrons leaving the gun? Leaving the cathode ray tube. And don't forget to square root. Sarah, what'd you get? I heard 2.
2 times 10 to the, I forgot. 2 times 10 to the 2.1.
I don't think that's right. Is that 2.1 times 10 to the 7th? Just because 2.1 times 10 to the 8th is close enough to the speed of light that I'd be proud to achieve that in a particle accelerator, let alone I just, that number, I don't think we get an electron going that fast. Okay. 7th, yeah, that's still 10 times slower. Lots of room. Okay. Jess, what's B want me to find? What does it want me to find? You know what? That's in the deflection section right here, and I'll even tell you, I think it's going to be up because the up is positive. Okay, so vertical. Vertical what? How am I going to do acceleration? Any suggestions? Now I'm just running through what things that I know that have acceleration in it. What things do I know that have acceleration in it? Ah! Nothing. Oh, I got a blink out of him. Did you hear what Amanda said? First, I got to try something, Jess. I'm not going to freeze up. First thing I might try is, well, maybe F equals MA. Before I went any further, I would now say to myself, Jess, how would I get the A by itself? Do I know the M? It's an electron. Okay, that alone suggests maybe I'm on the right track. Which force? Isn't it electric force? Because it's being deflected by those plates. So now I'm back in this unit, and I'm looking for the equations that have force in them. One says KQ1 Q2 over R squared. That's what I use when I have two charges. Do I have two different charges in this question? Nope. Oh, Jess, there's another equation that has an F in it. Can you get the F by itself, please? I like to write QE because that way it looks a lot more like mg from gravity. I'm trying to relate everything to stuff I kind of know already. So QE equals MA. Cool. Do I know Q? It's an electron. Oh. Do I know the electric field? Say no. Wait a minute. Is there a way that I can calculate the electric field if I know the distance and the voltage? Yeah, you're looking at your formula sheet again. You're trying to see if there's an electric field equation that has voltage and distance in it that doesn't have a voltage or a distance in it. Yes. Okay. By the way you also know don't use the KQ over R squared. The fact you said R means what's causing the electric field should be something around what's causing the electric field with plates. You with me so far? So if I hear you correctly, you tell me I can go Q, change in voltage over distance equals MA. How did you say to get the A by itself, Jess? Do you mind? I'm going to do that right now and stuck that down there. Do I know Q? It's an electron. Do I know the voltage? Look at the picture. Do I know M? It's an electron. Do I know D? Look at the picture. Ha! We're good with this. This will work. This will work. This will work. The acceleration is going to be 1.6 times 10 to the negative 19. What was the voltage? I've scrolled down. The voltage? 7? No. Okay. That's a sloppy, silly, in my mind, mistake. If this was multiple choice, you better believe one of the answers that I would have to pick from would be using that 1200 as well. It's the deflecting volt. It's got to be 750. Yeah. Mass, 9.11 times 10 to the negative 31. And the distance, please don't say 2. 0.02. All right. What's the vertical acceleration? What do you get? 6.6 times 10 to the 15th? And that's an acceleration, not a speed, so that can be magnitude larger than light because the acceleration has nothing to do with the speed of light. Meters per second squared. C. Hayden, what's C asking me to find? To do what?
Pass through the
Oh, C wants me to find that time. First question. What was the vertical acceleration we just calculated? There was a vertical acceleration. Is there a horizontal acceleration at all? Is there anything in this area here causing it to speed up or slow down horizontally at all? Nope. Nope. So you ready? First thing I'm going to make a little note is AX is 0. Why is that so nice? Hayden, what does the question want me to find? See, I think I would go like this. D equals VT plus a half AT squared. They really, look up, Hayden, they want me to find the horizontal time to travel the horizontal distance, but since the horizontal acceleration is nothing, it's really D equals VT. How to get the T by itself? The time to go horizontally is going to be the horizontal distance divided by the horizontal velocity. What is the horizontal? Please read carefully. What is the horizontal distance? Thank you, 0.05. What is the horizontal velocity or speed? No, otherwise it wouldn't be going anywhere. You mean that's why I had to do A? 2.1 times 10 to the 7th? How long will it take to travel sideways? Do you get 2.38 times 10 to the negative 9? I'll even go 2.4 times 10 to the negative 9 seconds. Is that a lot of time, Hayden? No, it's a very small amount of time. By the way, it's such a small amount of time that we can ignore gravity, even though technically gravity is pulling down on the electron. You could actually work out, if you're bored, how much that electron is going to fall. I think it's less than the actual width of a proton. Like, it's not going to fall. Meh. Okay? So, Hayden, how long does it take to go from here to here? How long is it deflected for? Same answer. Same answer. You could actually calculate, since you know now you know time and you know acceleration, you could calculate by how many centimeters it's deflected, and now you're already starting to be able to aim exactly. In fact, you can actually calculate the angle theta that you want to aim it to if you really want to. We used to do this as an extension. We would calculate the angle theta. Well, first of all, we would calculate the vertical change in distance with the acceleration of the time. You could calculate angle theta, and you could then figure out where it was going to hit the screen. It's a few more lines. I don't dive that deep into it because none of your TVs work this way anymore, sadly. What's your homework? Number 1, 2, skip 3, 4, 5, 7, skip 6 since I never included it for some reason. So 1, 3, 4, 5, 7, 12, 14, and you can now do every question on the ultimate review. We're finished. Friday is going to be nothing but review. Your test is going to be a week from today. It's going to be Wednesday. Friday, you're going to get a take-home quiz. We'll mark it Monday. Test Wednesday. Test Wednesday, rather than doing it after the May long weekend, we want to do it before the May long weekend. Okay?